Imagine a star so dense that a single teaspoon of its material would weigh billions of tons. Now picture that star spinning hundreds of times per second, sending out beams of radiation like a cosmic lighthouse. This isn't science fiction, it's the reality of neutron stars and pulsars, some of the most extreme and mysterious objects in the universe. These stellar remnants are born from the explosive deaths of massive stars, yet they hold secrets that even the brightest minds in astrophysics are still trying to unravel. From their mind-bending density to their unimaginable magnetic fields, neutron stars and pulsars challenge everything we think we know about the laws of physics. Why do some pulsars suddenly speed up? What causes the mysterious fast radio bursts linked to these objects? And could some neutron stars actually be made of something even stranger, like free quarks? In this video, we're diving deep into the cosmos to explore 25 of the most fascinating mysteries surrounding neutron stars and pulsars. These enigmatic objects aren't just scientific curiosities, they're cosmic laboratories that push the boundaries of our understanding. So, buckle up and get ready to journey into the heart of some of the universe's most extreme phenomena. By the end of this video, you'll not only have a newfound appreciation for these celestial wonders, but also a glimpse into the questions that keep astronomers awake at night. Let's begin. Now, let's step into the fiery crucible of a supernova where the story of neutron stars begins. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, it faces a catastrophic end. The star's core, no longer able to withstand the crushing force of its own gravity, collapses in on itself. This collapse happens in a matter of seconds, triggering a supernova explosion so powerful that it outshines entire galaxies. But within this chaos, something extraordinary is born: a neutron star. As the core collapses, protons and electrons are forced together, merging into neutrons. The result is an incredibly dense object, packing the mass of 1.4 suns into a sphere no wider than a city. Yet not all supernovae leave behind neutron stars. Some fail to produce them entirely, and scientists are still trying to understand why. What conditions must be met for a neutron star to form? Why do some collapsing stars instead create black holes? These questions remain at the heart of one of the universe's greatest mysteries. The birth of a neutron star is a delicate balance of forces. If the collapsing core is too massive, it will continue to collapse into a black hole. If it's too light, it may not form a neutron star at all. And even when conditions seem perfect, the process is so violent and complex that predicting the outcome is incredibly challenging. This uncertainty makes the birth of neutron stars one of the most fascinating and unresolved puzzles in astrophysics. As we move forward, we'll explore how these newborn neutron stars behave, but for now, let's marvel at the sheer power and mystery of their creation. The universe has a way of turning destruction into something extraordinary, and neutron stars are a perfect example of that cosmic alchemy. Now, let's dive into the astonishing density of neutron stars, a feature that makes them some of the most extreme objects in the universe. Imagine taking a single teaspoon of material from a neutron star. That tiny amount would weigh billions of tons, more than the combined weight of every car, building, and mountain on Earth. This incredible density is a result of the star's core being packed with neutrons, squeezed together so tightly that the space between them is almost non-existent. But how does matter behave under such extreme conditions? This is one of the biggest mysteries in astrophysics. Inside a neutron star, the pressure is so immense that atoms can't exist in their normal form. Instead, protons and electrons are crushed together, forming a sea of neutrons. Scientists call this state neutron degenerate matter, but even this term doesn't fully capture the bizarre nature of what's happening. The rules of physics as we know them begin to break down, and predicting how matter behaves becomes a monumental challenge. one of the key questions scientists are trying to answer is whether neutron stars contain even stranger forms of matter. Some theories suggest that their cores might be made of exotic particles like quarks, which are the building blocks of protons and neutrons. Others propose that the intense pressure could create a superfluid, a state of matter that flows without any friction. These ideas are fascinating, but they're also incredibly difficult to test. Neutron stars are so dense and distant that studying their interiors directly is nearly impossible. To make matters even more complex, the extreme conditions inside neutron stars push the limits of our understanding of quantum mechanics and general relativity. Scientists rely on computer simulations and theoretical models to explore these environments, but even the most advanced technology can't fully replicate the conditions inside a neutron star. This leaves us with a tantalizing mystery. What exactly lies at the heart of these cosmic powerhouses? As we continue to unravel the secrets of neutron stars, their density remains one of the most awe-inspiring and perplexing aspects of their nature. It's a reminder of just how much we still have to learn about the universe and the extraordinary forces that shape it. Next, we'll explore another fascinating mystery, the incredible rotational speeds of pulsars and how they manage to spin so fast without tearing themselves apart. Now turning to the astonishing speeds of pulsars, we encounter another mind-bending mystery of these cosmic wonders. Pulsars, a type of neutron star, are known for their dizzying rotational speeds, with some spinning hundreds of times every single second. To put that into perspective, imagine an object the size of a city completing a full rotation faster than the blink of an eye. It's a feat that defies our everyday understanding of physics and raises a critical question: how do pulsars spin so fast without tearing themselves apart? The answer lies in their incredible density and the immense gravitational forces at play. A pulsar's rapid spin is a remnant of its birth during a supernova explosion. As the core of a massive star collapses, it conserves the original star's angular momentum, much like a figure skater pulling in their arms to spin faster. This process results in a neutron star spinning at breakneck speeds. But what keeps these stars from flying apart under such extreme forces? The key is their unimaginable density. The gravitational pull of a pulsar is so strong that it counteracts the outward force generated by its rotation, holding the star together even as it spins at hundreds of revolutions per second. Yet, this rapid rotation doesn't last forever. Over time, pulsars slow down, and scientists are still unraveling the mechanisms behind this gradual deceleration. One leading theory involves the emission of electromagnetic radiation. As pulsars spin, they emit beams of radiation from their magnetic poles. This radiation carries away energy, causing the star to lose rotational speed over millions of years. Another factor could be the interaction between the pulsar's magnetic field and its surrounding environment, such as a disk of debris or a companion star. These interactions can create drag, further slowing the pulsar's spin, but the mystery deepens when we consider pulsars that don't follow this expected pattern. Some pulsars, known as millisecond pulsars, spin even faster hundreds of times per second and show little sign of slowing down. These outliers challenge our understanding of pulsar evolution. Scientists believe they may have been recycled, gaining speed by accreting matter from a companion star. This process transfers angular momentum to the pulsar, effectively spinning it up like a cosmic top. The study of pulsar speeds not only sheds light on the behavior of these extreme objects, but also provides a window into the fundamental laws of physics. By observing how pulsars spin and slow down, scientists can test theories about gravity, electromagnetism, and the behavior of matter under conditions that are impossible to replicate on Earth. As we continue to explore these spinning marvels, we're reminded of the universe's capacity to surprise and challenge us, pushing the boundaries of what we thought was possible. Next, we'll delve into the extreme magnetic fields of magnetars, another fascinating mystery that reveals the incredible forces at work in the cosmos. Now shifting our focus to the magnetic marvels of the cosmos, we encounter magnetars, a rare and extraordinary type of neutron star. These celestial objects possess magnetic fields so powerful they defy comprehension trillions of times stronger than Earth's magnetic field. To put this into perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would erase the data from every credit card on our planet. Such immense forces raise a profound question. How do magnetars generate these unimaginably strong magnetic fields? The answer lies in the chaotic aftermath of a supernova explosion. When a massive star collapses, its core is compressed into a neutron star, and under certain conditions, the star's magnetic field becomes amplified to extreme levels. Scientists believe that the rapid rotation and turbulent dynamics of the collapsing star play a crucial role in this process. As the star's core spins and twists, its magnetic field lines become tightly wound, creating a magnetic powerhouse. However, the exact mechanisms behind this amplification remain one of the great mysteries of astrophysics. The impact of a magnetar's magnetic field on its surroundings is nothing short of dramatic. These fields are so intense that they can distort the very fabric of space-time, creating ripples that could theoretically be detected as gravitational waves. Additionally, magnetars are known to produce bursts of X-rays and gamma rays, some of which are so powerful they can be detected across the universe. These bursts occur when the star's crust undergoes sudden shifts, releasing vast amounts of energy in the process. Such events, known as starquakes, are thought to be triggered by the immense stress exerted by the magnetic field on the star's surface. But the influence of magnetars extends far beyond their immediate vicinity. Their magnetic fields can interact with surrounding matter, creating shock waves that heat up nearby gas and dust. In some cases, these interactions can even trigger the formation of new stars. Yet, despite their immense power, magnetars are relatively short-lived. Their magnetic fields decay over time, and the star's activity gradually diminishes. This raises another intriguing question. What happens to a magnetar as its magnetic field weakens? Does it transform into a more typical neutron star, or does it follow a different evolutionary path? The study of magnetars not only deepens our understanding of neutron stars, but also provides insights into some of the most extreme conditions in the universe. By observing these magnetic giants, scientists can explore the limits of physical laws and test theories about the behavior of matter and energy under conditions that are impossible to replicate on Earth. As we continue to unravel the mysteries of magnetars, we are reminded of the universe's capacity to astonish and challenge our understanding of the cosmos. Next, we'll explore the puzzling phenomenon of glitches in pulsar timing, where these cosmic clocks suddenly speed up, leaving scientists searching for answers. Now turning to the enigmatic behavior of pulsars, we encounter a phenomenon that has puzzled astronomers for decades: the mysterious glitches in pulsar timing. Pulsars, often referred to as cosmic lighthouses, are known for their incredibly precise rotation, emitting beams of radiation at regular intervals. However, occasionally, these celestial clocks experience sudden, unexpected increases in their rotational speed. These events, known as glitches, can last for mere seconds or persist for days, leaving scientists scrambling to understand their cause. One leading theory suggests that these glitches are the result of starquakes, sudden shifts in the pulsar's crust caused by the immense stress of its rapid rotation and powerful magnetic fields. Just as tectonic plates on Earth can shift and cause earthquakes, the crust of a neutron star may crack and rearrange itself, releasing energy that briefly speeds up the star's rotation. Another possibility is that changes in the star's interior, such as the movement of superfluid neutrons, could be responsible. In the dense core of a neutron star, neutrons are thought to behave like a frictionless fluid, flowing freely and potentially transferring angular momentum to the star's crust, causing it to spin faster. Yet another intriguing explanation involves interactions with external objects. Some pulsars are part of binary systems, orbiting another star or even a black hole. The gravitational pull of a companion object could potentially disrupt the pulsar's rotation, leading to a glitch. Alternatively, the accretion of matter from a nearby star could alter the pulsar's spin, though this scenario is less common for isolated pulsars. The study of pulsar glitches offers a unique window into the internal structure and dynamics of neutron stars. By analyzing the timing and magnitude of these events, scientists can infer details about the star's interior, such as the density and behavior of its superfluid core. However, despite decades of observation, the exact mechanisms behind pulsar glitches remain elusive. Each glitch provides a new piece of the puzzle, but the full picture is yet to be revealed. As we continue to monitor these cosmic timekeepers, the mystery of pulsar glitches serves as a reminder of the complexity and unpredictability of the universe. Next, we'll delve into the connection between neutron stars and fast radio bursts, exploring how these fleeting cosmic signals might hold the key to unlocking even more secrets of the cosmos. Now shifting our gaze to one of the most fleeting and enigmatic phenomena in the cosmos, we encounter fast radio bursts, or FRB. These mysterious bursts of radio waves last only milliseconds, yet they release as much energy as the sun does in days. First discovered in 2007, FRBs have since become one of the most tantalizing puzzles in modern astrophysics. But what exactly causes these brief, intense flashes of radio energy? And could neutron stars, particularly magnetars, be the culprits? One of the leading theories points to magnetars, a type of neutron star with magnetic fields trillions of times stronger than Earth. These extreme magnetic fields can create immense stress on the star's surface, potentially triggering violent eruptions of energy. In fact, in 2020, astronomers detected an FRB originating from a magnetar within our own galaxy, providing the first direct evidence linking these cosmic powerhouses to fast radio bursts. This discovery has fueled speculation that magnetars could be responsible for at least some of the FRBs we observe across the universe, but the story doesn't end there. While magnetars are strong candidates, they may not be the only source of FRBs. Some bursts appear to repeat, while others are one-time events, suggesting multiple origins. For instance, collisions between neutron stars or the interaction of neutron stars with black holes could also generate these intense radio signals. Additionally, some scientists have proposed more exotic explanations, such as the collapse of highly magnetized neutron stars or even the activity of advanced extraterrestrial civilizations, though the latter remains highly speculative. The challenge in unraveling the mystery of FRBs lies in their fleeting nature. By the time telescopes detect these bursts, they've already vanished, leaving behind only a faint trace of their existence. To overcome this, astronomers are deploying advanced radio telescopes and networks capable of pinpointing the exact locations of FRBs in the sky. These efforts are not only helping to identify potential sources, but also providing clues about the environments in which these bursts occur. As we piece together the puzzle of fast radio bursts, we're reminded of how much we still have to learn about the universe's most extreme objects. Whether they originate from magnetars, neutron star collisions, or something entirely unexpected, FRBs continue to challenge our understanding of the cosmos. Next, we'll explore the intriguing hypothesis that some neutron stars might not be made of neutrons at all, but rather of free quarks, opening the door to an entirely new class of stellar objects. Now turning to a fascinating and speculative idea that challenges our understanding of neutron stars, we explore the quark star hypothesis. Could some of these dense stellar remnants actually be made of something even more exotic than neutrons? Imagine a star where the crushing forces of gravity are so immense that they break down neutrons themselves, releasing their fundamental building blocks, quarks. These hypothetical objects, known as quark stars, would be composed of free quarks, the particles that make up protons and neutrons. But do they really exist? And if so, how would they differ from the neutron stars we know? The concept of quark stars arises from the extreme conditions found in neutron stars. Under normal circumstances, neutrons remain stable, but in the core of a neutron star where pressures are unimaginably high, it's possible that neutrons could dissolve into their constituent quarks. This would create a state of matter unlike anything we've observed directly, a quark-gluon plasma, where quarks roam freely instead of being confined within particles. If such stars exist, they would represent a new class of stellar objects, bridging the gap between neutron stars and black holes. One of the key mysteries surrounding quark stars is how to distinguish them from traditional neutron stars. Both would appear incredibly dense and compact, but quark stars might have slightly different properties. For instance, they could be smaller and denser than neutron stars, with a smoother surface due to the absence of a solid crust. Additionally, their cooling rates might differ, as the behavior of free quarks could lead to unique thermal emissions. Detecting these subtle differences, however, is no easy task, as the extreme environments of these stars make direct observation nearly impossible. The search for quark stars has led scientists to study unusual neutron stars that don't quite fit the expected models. Some candidates, like the object known as RxJ 1856.5-3754, exhibit properties that could hint at a quark core. Yet, without definitive evidence, the existence of quark stars remains one of the great unsolved mysteries in astrophysics. Are they real, or are they just a theoretical possibility? The answer could reshape our understanding of matter under the most extreme conditions. As we ponder the quark star hypothesis, we're reminded of how much we still have to learn about the universe's most extreme objects. Whether these stars exist or not, the idea pushes the boundaries of our knowledge, challenging us to rethink what's possible in the cosmos. Next, we'll delve into another intriguing mystery: how neutron stars cool over time and why some appear to cool faster than our models predict. Now shifting our focus to another captivating mystery, let's explore how neutron stars cool over time and why some defy our expectations. Neutron stars are born scorching hot, with temperatures reaching hundreds of billions of degrees. Yet, as they age, they gradually lose heat, cooling down over millions of years. But here's the twist: not all neutron stars cool at the same rate. Some seem to shed their heat far faster than our models predict, leaving scientists puzzled about what's really happening inside these dense stellar remnants. The cooling process of neutron stars is governed by the complex interplay of particles and forces within their cores. In the early stages, neutrinos, tiny, nearly massless particles, carry away most of the heat, allowing the star to cool rapidly. Over time, as the star ages, this neutrino-driven cooling slows down, and the star begins to lose heat primarily through surface radiation. But observations have revealed that some neutron stars cool much faster than this standard model suggests, hinting at the presence of exotic particles or unknown processes at work. One possibility is that exotic particles such as pions or kaons could be forming in the star's core. These particles might enhance the cooling process by allowing neutrinos to escape more efficiently. Another intriguing idea involves the presence of quark matter, which we touched on earlier. If the core of a neutron star transitions into a quark-gluon plasma, it could significantly alter the star's cooling behavior. These exotic states of matter could explain why some neutron stars cool faster than expected, but detecting them remains a formidable challenge. Adding to the mystery, some neutron stars exhibit sudden drops in temperature, as if they're cooling in fits and starts. This erratic behavior suggests that internal processes, such as starquakes or changes in the star's magnetic field, might also play a role in regulating heat loss. Understanding these mechanisms could provide crucial insights into the inner workings of neutron stars, shedding light on the exotic physics that govern their behavior. The cooling mystery of neutron stars isn't just a theoretical puzzle, it's a window into the extreme conditions that exist nowhere else in the universe. By studying how these stars lose heat, scientists hope to uncover new clues about the nature of matter under unimaginable pressures. As we continue to probe this enigma, we're reminded that even the most well-studied objects in the cosmos still hold secrets waiting to be unraveled. Next, we'll turn our attention to the strange behavior of X-ray pulsars and the mysteries they present. Now turning to the enigmatic world of X-ray pulsars, we encounter a phenomenon that defies our expectations yet again. These celestial objects are not your ordinary pulsars. They are powerhouses of X-ray radiation, emitting intense beams of energy that can outshine entire galaxies. But what makes X-ray pulsars so peculiar, and why do they behave in such strange and unpredictable ways? The answer lies in their relationship with companion stars and the intricate dance of matter and energy that unfolds between them. X-ray pulsars are often found in binary systems where they orbit a companion star. This companion, usually a massive star, plays a crucial role in fueling the pulsar's intense X-ray emissions. As the companion star evolves, it begins to shed its outer layers, releasing streams of gas into space. This gas doesn't simply drift away, it gets pulled in by the pulsar's immense gravitational pull, spiraling toward its surface in a process known as accretion. As the gas falls onto the pulsar, it heats up to millions of degrees, emitting the powerful X-rays that make these objects so fascinating. But here's where the mystery deepens. The process of accretion isn't always smooth or steady. Sometimes the flow of gas becomes erratic, leading to sudden bursts of X-ray activity. At other times, the pulsar seems to turn off, its X-ray emissions dropping to almost undetectable levels. Scientists are still trying to understand what causes these fluctuations. Is it due to changes in the companion star's behavior, or are there internal mechanisms within the pulsar itself that regulate the flow of matter? One leading theory suggests that the pulsar's magnetic field plays a key role in shaping its X-ray emissions. As the accreted gas approaches the pulsar, it interacts with the star's powerful magnetic field, which channels the gas toward the magnetic poles. This creates hotspots on the pulsar's surface where the X-rays are emitted. However, if the magnetic field becomes unstable or shifts, it could disrupt the flow of gas, leading to the erratic behavior we observe. Another intriguing aspect of X-ray pulsars is their ability to recycle themselves. In some cases, a pulsar can accrete enough matter from its companion to spin faster, rejuvenating its rotation and X-ray emissions. This process, known as spin-up, can transform an old, slow-spinning pulsar into a young, energetic one. But how exactly this happens and why it doesn't occur in all X-ray pulsars remains a mystery. The strange behavior of X-ray pulsars isn't just a curiosity. It's a window into the extreme physics of matter, energy, and magnetic fields in the universe. By studying these enigmatic objects, scientists hope to uncover new insights into the processes that govern the cosmos. As we continue to explore the mysteries of X-ray pulsars, we're reminded that even the most well-studied phenomena can still surprise us. Next, we'll delve into the rare and dramatic collisions of neutron stars and the secrets they reveal about the universe. Now shifting our gaze to one of the most cataclysmic events in the cosmos, we explore the rare and awe-inspiring collisions of neutron stars. These monumental encounters are not just spectacular to witness, they are cosmic factories, producing gravitational waves and forging heavy elements like gold, platinum, and uranium. But what exactly happens when two neutron stars collide, and how do these collisions shape the universe as we know it? When two neutron stars spiral toward each other, locked in a deadly dance by gravity, the collision is nothing short of explosive. The immense density and energy involved create ripples in spacetime, known as gravitational waves, which were first detected in 2017 by observatories like LIGO and Virgo. These waves carry with them the story of the collision, offering scientists a unique way to study these events in unprecedented detail. But the drama doesn't end there. The collision also triggers a burst of gamma rays, one of the most energetic phenomena in the universe, and a glowing afterglow of light across multiple wavelengths, known as a kilonova. One of the greatest mysteries surrounding neutron star collisions is what happens in the moments immediately after the impact. The extreme conditions, temperatures reaching trillions of degrees and pressures far beyond anything we can replicate on Earth, create a cosmic crucible where matter is transformed. It's here that heavy elements like gold and platinum are forged through a process called rapid neutron capture, or the R process. This process, which occurs in mere seconds, is responsible for creating many of the precious metals found on Earth and throughout the universe. Yet, scientists are still piecing together how exactly this process unfolds and why it produces such a specific mix of elements. Another puzzle is the aftermath of these collisions. What remains after two neutron stars collide? In some cases, the merger may result in a new, more massive neutron star. However, if the combined mass is too great, it could collapse into a black hole, swallowing the remnants of the collision. The exact threshold for this transformation and the conditions that determine the outcome are still not fully understood. Additionally, the ejected material from the collision spreads out into space, enriching the surrounding interstellar medium with heavy elements. This cosmic recycling plays a crucial role in the evolution of galaxies, seeding future generations of stars and planets with the building blocks of life. The study of neutron star collisions also raises questions about their frequency and impact on the universe. While these events are rare, occurring perhaps once every 100,000 years in a galaxy like our own, their cumulative effect over billions of years is profound. They contribute to the chemical diversity of the cosmos and may even influence the formation of planetary systems capable of supporting life. Yet, many aspects of these collisions remain shrouded in mystery, from the exact mechanisms of element formation to the long-term consequences of the ejected material. As we continue to observe and analyze these extraordinary events, each collision offers a new piece of the puzzle, bringing us closer to understanding the forces that shape our universe. The mystery of neutron star collisions reminds us that even the most violent events in the cosmos can have a profound and lasting impact, weaving the story of the universe in ways we are only beginning to comprehend. Next, we'll uncover the puzzling absence of pulsars in some supernova remnants and what it tells us about the life cycles of these stellar remnants. Now turning to another intriguing puzzle in the cosmos, we delve into the mystery of the missing pulsars in supernova remnants. When a massive star explodes in a supernova, it often leaves behind a dense, rapidly spinning neutron star known as a pulsar. These pulsars emit beams of radiation that sweep across space like cosmic lighthouses, making them detectable from Earth. Yet, not all supernova remnants have a visible pulsar at their core. Why is this the case, and what could be hiding these stellar remnants from our view? One possibility is that the pulsar is simply too faint for us to detect. Pulsars emit radiation in specific patterns, and if their beams are not pointed toward Earth, they can appear invisible to our telescopes. This phenomenon, known as the lighthouse effect, means that even if a pulsar exists within a supernova remnant, we might not see it simply because its light isn't shining in our direction. Over time, as the pulsar's rotation slows and its beams weaken, it could become even harder to detect, leaving the remnant seemingly empty. Another theory suggests that some pulsars might be moving too fast to stay within their supernova remnants. When a neutron star is born, the explosion can give it a powerful kick, propelling it at incredible speeds, sometimes hundreds of kilometers per second. If the pulsar is moving fast enough, it could escape the confines of the remnant entirely, leaving behind a shell of debris with no visible central object. This runaway pulsar would then drift through space far from the site of its birth, making it difficult to link it back to its original supernova. A third explanation involves the pulsar's emission pattern changing over time. Some pulsars might transition into a state where they emit less radiation or switch to a different wavelength that our current instruments cannot easily detect. For example, a pulsar might evolve into a quieter phase, emitting only sporadic bursts of energy or shifting its emissions to frequencies that are harder to observe. In such cases, the pulsar would still exist, but it would no longer be visible in the way we expect, leaving the supernova remnant seemingly devoid of its central star. The absence of pulsars in some supernova remnants also raises questions about the diversity of neutron stars. Could some supernova produce neutron stars that don't behave like typical pulsars? Perhaps these remnants harbor exotic objects such as magnetars with ultra-strong magnetic fields or even quark stars, which might emit radiation in ways we don't yet understand. The search for these missing pulsars challenges our understanding of neutron star formation and evolution, pushing scientists to refine their models and develop new observational techniques. As we continue to study these enigmatic remnants, each discovery brings us closer to unraveling the mystery of the missing pulsars. Whether they are too faint, too fast, or simply too different from what we expect, these hidden objects remind us that the universe is full of surprises. Next, we'll explore the nature of neutron star crusts and how these incredibly dense layers hold clues to the inner workings of these stellar remnants. Now shifting our focus to the outer layers of these cosmic giants, let's explore the nature of neutron star crusts. These crusts are unlike anything we encounter on Earth. Imagine a material so dense that a sugar cube-sized piece would weigh as much as a mountain. Yet, despite their incredible density, neutron star crusts are also remarkably strong and flexible, capable of withstanding forces that would obliterate any known substance on our planet. But how do these crusts behave under such extreme conditions, and what secrets do they hold about the star's mysterious interior? The crust of a neutron star is thought to be a solid layer, just a few kilometers thick, sitting atop a sea of superfluid neutrons. This crust is composed of atomic nuclei packed so tightly together that they form a lattice structure, held in place by the immense gravitational pull of the star. But here's the twist: this lattice isn't rigid like a crystal. Instead, it can bend, stretch, and even crack under the immense pressures and stresses it endures. These deformations can lead to starquakes, sudden shifts in the crust that release enormous amounts of energy, sometimes even altering the star's rotation. One of the biggest mysteries surrounding neutron star crusts is how they manage to remain intact despite the extreme conditions. The pressure at the base of the crust is so intense that it approaches the limits of what matter can endure. Scientists believe that the crust's strength comes from the unique properties of neutron-rich matter, which behaves differently from ordinary atomic nuclei. Yet, even with this strength, the crust isn't invincible. When the star's magnetic field interacts with the crust, it can cause the lattice to fracture, leading to the release of bursts of energy that we observe as X-ray or gamma-ray flares. Another intriguing aspect of neutron star crusts is their role in revealing the star's interior. By studying how the crust deforms and vibrates, scientists can infer details about the star's core, such as its density and composition. For example, the way the crust responds to a starquake can provide clues about the superfluid neutrons beneath it, offering a glimpse into the exotic physics at play in the star's depths. These observations are helping researchers refine their models of neutron star interiors, bringing us closer to understanding the behavior of matter under the most extreme conditions in the universe. The study of neutron star crusts also raises questions about their long-term stability. Over millions of years, the crust could undergo gradual changes, such as the buildup of stress or the accumulation of heavier elements sinking toward the core. These processes might eventually lead to dramatic events, like the collapse of the crust or the formation of exotic states of matter. Understanding these dynamics is crucial for piecing together the life cycle of neutron stars and predicting their ultimate fate. As we continue to probe the mysteries of neutron star crusts, each discovery sheds light on the incredible resilience and complexity of these stellar remnants. From their ability to withstand unimaginable pressures to their role as windows into the star's interior, neutron star crusts are a testament to the strange and fascinating nature of the cosmos. Next, we'll turn our attention to the thin atmospheres that envelop these stars and the secrets they hold about the surface conditions of neutron stars. Now turning to the thin, enigmatic atmospheres of neutron stars, we find yet another layer of mystery surrounding these cosmic powerhouses. Unlike the thick, gaseous atmospheres of planets or even stars like our Sun, neutron star atmospheres are incredibly thin, often just a few centimeters deep. Yet, despite their minimal size, these atmospheres play a crucial role in shaping how neutron stars emit light and interact with their surroundings. So, what exactly are these atmospheres made of, and how do they influence the star's appearance and behavior? The composition of neutron star atmospheres is one of the most puzzling aspects of their study. Scientists believe these atmospheres are primarily made up of hydrogen or helium, but the extreme conditions on the star's surface can cause these elements to behave in ways that defy our everyday understanding of matter. For instance, the intense gravitational pull of a neutron star can compress these gases into a state so dense that they form a kind of superfluid layer, where atoms are packed tightly together and move with almost no friction. This unique state of matter can significantly alter how light is emitted from the star's surface, creating patterns that are unlike anything seen in other celestial objects. One of the key mysteries surrounding neutron star atmospheres is how they affect the star's emission of light. Neutron stars are known for their intense X-ray and gamma-ray emissions, but the atmosphere plays a critical role in filtering and shaping this radiation. As light passes through the atmosphere, it interacts with the densely packed atoms, causing some wavelengths to be absorbed while others are amplified. This process can create distinct spectral signatures that scientists use to study the star's surface temperature, magnetic field, and even its rotation rate. However, the exact mechanisms behind these interactions remain poorly understood, leaving researchers to piece together clues from observations and theoretical models. Another intriguing aspect of neutron star atmospheres is their ability to reveal details about the star's surface. Because the atmosphere is so thin, it acts like a window into the underlying layers of the star. By analyzing the light that passes through the atmosphere, scientists can infer the composition and structure of the star's surface, including the presence of exotic materials like iron or even free-floating neutrons. These observations provide valuable insights into the extreme conditions that exist on neutron stars, helping researchers refine their understanding of how matter behaves under such intense pressures and temperatures. The study of neutron star atmospheres also raises questions about their stability and evolution over time. Given the extreme environment, these atmospheres are constantly being bombarded by high-energy particles and radiation from the star's magnetic field. This bombardment can cause the atmosphere to heat up, expand, or even be stripped away entirely, leading to dramatic changes in the star's appearance and behavior. Understanding these processes is crucial for piecing together the life cycle of neutron stars and predicting how they will evolve over billions of years. As we continue to unravel the mysteries of neutron star atmospheres, each discovery brings us closer to understanding these extraordinary objects. From their role in shaping the star's light emissions to their ability to reveal the secrets of the star's surface, neutron star atmospheres are a fascinating frontier in astrophysics. Next, we'll explore the theoretical limits of neutron star masses and the intriguing questions they raise about the nature of matter in the universe. Now shifting our focus to the intriguing puzzle of neutron star mass limits, we encounter one of the most fundamental questions in astrophysics. How heavy or light can a neutron star actually be? Neutron stars are not just cosmic oddities, they are laboratories for testing the extremes of physics, and their masses hold the key to understanding the behavior of matter under conditions we can scarcely imagine. But why do these stars seem to obey strict mass limits, and what happens when they approach these boundaries? At the heart of this mystery lies the delicate balance between gravity and the forces that hold matter together. Neutron stars are born from the collapse of massive stars, and their cores are so dense that protons and electrons merge to form neutrons. This creates an object so compact that a single teaspoon of its material would weigh billions of tons. But even these extreme objects have limits. Scientists have determined that neutron stars must fall within a specific mass range, typically between about 1.4 and 2.2 times the mass of our Sun. Below this range, the star wouldn't have enough gravity to sustain its structure, and above it, the star would collapse into a black hole. The lower mass limit is particularly fascinating. If a neutron star were to dip below about 1.4 solar masses, it would no longer have the gravitational pull needed to keep its neutrons tightly packed. Instead, it might revert to a less dense state, possibly becoming a white dwarf or even disintegrating entirely. This raises the question, why haven't we observed any neutron stars below this limit? Are they simply too faint to detect, or do they not exist at all? The answer could lie in the complex physics of stellar evolution and the conditions required for neutron star formation. On the other end of the spectrum, the upper mass limit is equally puzzling. When a neutron star approaches about 2.2 solar masses, the immense gravitational pressure overwhelms the forces that keep neutrons from collapsing further. At this point, the star can no longer support itself, and it implodes, forming a black hole. But why does this threshold exist, and what determines its exact value? The answer lies in the realm of quantum chromodynamics, the theory that describes how quarks and gluons interact within atomic nuclei. In neutron stars, these interactions become incredibly complex as the extreme density forces particles into states that defy our current understanding of physics. One of the most intriguing aspects of this mystery is the role of exotic matter. Some theories suggest that at the upper mass limit, the neutrons in a neutron star might break down into their constituent quarks, forming a quark star. This hypothetical object would be even denser than a neutron star, but its existence remains unconfirmed. If quark stars do exist, they could help explain why neutron stars seem to have a strict upper mass limit, as the transition from neutrons to quarks might stabilize the star just before it collapses into a black hole. The study of neutron star mass limits is not just an academic exercise. It has profound implications for our understanding of the universe. By determining these limits, scientists can gain insights into the nature of matter at its most extreme, the behavior of gravity in intense environments, and even the formation of black holes. Each observation of a neutron star, whether it's at the lower or upper end of the mass spectrum, brings us closer to unraveling these cosmic mysteries. As we continue to probe the limits of neutron star masses, we are reminded of how much we still have to learn about these extraordinary objects. From the delicate balance of forces that define their existence to the exotic states of matter that may lie within them, neutron stars challenge our understanding of the universe in ways that few other objects can. Next, we'll delve into the powerful jets of particles emitted by some neutron stars and the mysteries surrounding their formation and behavior. Now turning to the enigmatic jets of particles that some neutron stars unleash into space, we find ourselves staring at one of the most dramatic and puzzling phenomena in the cosmos. These jets, streams of charged particles racing at nearly the speed of light, are not just awe-inspiring displays of cosmic power. They are also windows into the extreme physics at play within neutron stars. But what exactly causes these jets, and why do only certain neutron stars produce them? The answers lie in the intricate interplay of magnetic fields, rotation, and the star's environment. Neutron star jets are among the most energetic outflows in the universe, capable of stretching for light years across space. They are often observed in systems where the neutron star is paired with a companion star, siphoning material from its neighbor. As this material spirals toward the neutron star, it forms a swirling disk of gas and dust, heating up to incredible temperatures. The intense magnetic fields of the neutron star, combined with its rapid rotation, channel some of this material into narrow beams that shoot out from the star's poles. These beams are what we observe as jets, but here's the mystery: not all neutron stars produce jets. In fact, only a fraction of them do. Why is that? One possibility lies in the strength and orientation of the neutron star's magnetic field. Jets seem to be more common in neutron stars with highly ordered magnetic fields, where the field lines are aligned in a way that efficiently channels material into the poles. In contrast, neutron stars with chaotic or weaker magnetic fields may not be able to produce jets at all. Another factor could be the rate at which the neutron star is accreting material from its companion. Too little material, and there might not be enough energy to power the jets. Too much, and the system could become unstable, disrupting the jet formation process. The formation of these jets is also closely tied to the neutron star's rotation. Rapidly spinning neutron stars, particularly those known as millisecond pulsars, are more likely to produce jets. This is because their fast rotation helps to amplify the magnetic fields and accelerate particles to extreme speeds. However, even among these fast-spinning stars, not all produce jets, suggesting that other factors, such as the star's age or the composition of the accreted material, might also play a role. One of the most intriguing aspects of neutron star jets is their ability to influence their surroundings. These jets can carve out vast cavities in the surrounding interstellar medium, trigger star formation in nearby gas clouds, and even contribute to the chemical enrichment of galaxies by spewing out heavy elements. Yet, despite their profound impact, we still don't fully understand how they form or why they vary so much from one neutron star to another. The study of neutron star jets is not just about understanding these cosmic powerhouses. It's also about unraveling the fundamental processes that govern the universe. By examining how these jets form and evolve, scientists can gain insights into the behavior of matter and energy under extreme conditions, the dynamics of magnetic fields, and the interactions between neutron stars and their environments. Each observation of a neutron star jet brings us closer to solving this cosmic puzzle. As we continue to explore the mysteries of neutron star jets, we are reminded of the incredible diversity and complexity of these stellar remnants. From their formation to their impact on the cosmos, neutron star jets challenge our understanding of the universe in ways that few other phenomena can. Next, we'll investigate the oscillations or starquakes that occur on neutron stars and the mysteries surrounding their causes and effects. Now shifting our focus to the rhythmic tremors that ripple across the surfaces of neutron stars, we encounter the fascinating phenomenon of neutron star oscillations, often referred to as starquakes. These oscillations are not just subtle vibrations, they are powerful seismic events that can release immense amounts of energy, reshaping the star's surface and providing a unique glimpse into its hidden interior. But what exactly triggers these starquakes, and what can they tell us about the inner workings of these dense stellar remnants? Neutron star oscillations are thought to occur when the star's rigid crust, under immense pressure from the dense core, suddenly shifts or cracks. Imagine the crust of a neutron star as a thin, brittle shell, constantly strained by the intense gravitational forces and magnetic fields within. Over time, this strain builds up until the crust can no longer withstand the pressure, causing it to fracture and release energy in the form of oscillations. These events are akin to earthquakes on Earth but on a cosmic scale, with energies far beyond anything our planet could produce. One of the most intriguing aspects of these oscillations is what they reveal about the neutron star's interior. Just as seismologists use earthquakes to study Earth's inner layers, astronomers can analyze starquakes to probe the structure and composition of neutron stars. By measuring the frequencies and patterns of these oscillations, scientists can infer details about the star's density, the state of matter in its core, and even the strength of its magnetic field. This makes starquakes a powerful tool for understanding the extreme physics that govern neutron stars. However, the exact mechanisms behind these oscillations remain a mystery. Why do some neutron stars experience frequent starquakes while others seem relatively stable? One possibility is that the strength and orientation of the star's magnetic field play a crucial role. Neutron stars with highly twisted or unstable magnetic fields might be more prone to crustal fractures, leading to more frequent oscillations. Another factor could be the star's age and rotation rate. Younger, faster-spinning neutron stars might experience more stress on their crusts, making them more susceptible to starquakes. The study of neutron star oscillations also raises questions about the nature of the star's interior. Some theories suggest that the core of a neutron star might contain exotic states of matter, such as superfluids or quark-gluon plasma, which could influence the star's oscillations. If these exotic materials exist, they might produce unique oscillation patterns that could be detected by sensitive instruments. This opens up the possibility of using starquakes not just to study the crust, but to explore the deepest, most mysterious regions of the neutron star. Despite their destructive potential, starquakes also have a constructive side. The energy released during these events can heat the star's surface, causing it to emit bursts of X-rays or gamma rays that can be observed from Earth. These emissions provide valuable data for astronomers, helping them to map the star's surface and study its magnetic field. In some cases, starquakes have even been linked to changes in the star's rotation rate, offering clues about how neutron stars evolve over time. As we continue to unravel the mysteries of neutron star oscillations, we are reminded of the dynamic and ever-changing nature of these cosmic objects. From their violent origins to their ongoing evolution, neutron stars challenge our understanding of the universe in profound ways. Next, we'll explore the diverse range of companion objects that orbit neutron stars and the mysteries surrounding their formation and evolution. Now turning to the cosmic dance of neutron stars and their companions, we uncover another layer of intrigue in the universe. Neutron stars, these dense remnants of stellar explosions, are not always solitary wanderers. Many are found in the company of other celestial objects, ranging from planets to other stars, creating dynamic and often puzzling systems. But how do these companions come to orbit neutron stars, and what can they tell us about the life and evolution of these enigmatic objects? The companions of neutron stars are as varied as they are fascinating. Some neutron stars are paired with ordinary stars, forming binary systems where the two objects orbit each other in a delicate gravitational balance. In these systems, the neutron star often siphons material from its companion, creating intense bursts of X-rays and gamma rays that can be observed from Earth. Other neutron stars are accompanied by planets, some of which may have survived the violent supernova explosion that gave birth to the neutron star itself. These planetary companions raise intriguing questions about the resilience of worlds in the face of cosmic cataclysms. One of the greatest mysteries surrounding neutron star companions is how these systems form in the first place. In the case of binary systems, it's possible that both stars were born together, with one eventually exploding as a supernova and leaving behind a neutron star. However, the explosion would have released an enormous amount of energy, potentially disrupting the orbit of the surviving star. How, then, do some binary systems remain intact after such a violent event? scientists speculate that the companion star might have been far enough away to avoid being completely ejected, or that the neutron star's gravitational pull was strong enough to keep the system bound together. Planetary companions present an even greater puzzle. Could planets form around a neutron star after its birth, or are they remnants of the original star system that somehow endured the supernova? Some theories suggest that planets might form from the debris left behind by the explosion, while others propose that they could be captured from nearby star systems. The discovery of planets orbiting pulsars, a type of neutron star, has added fuel to this debate, as these planets seem to defy conventional models of planetary formation. The evolution of neutron star companion systems is another area of active research. Over time, the gravitational interactions between the neutron star and its companion can lead to dramatic changes. In binary systems, the neutron star's intense gravity can strip material from its companion, altering the companion's structure and even its fate. In some cases, this process can lead to the complete destruction of the companion star, leaving the neutron star alone once more. For planetary companions, the intense radiation and magnetic fields of the neutron star can erode their atmospheres or even tear them apart entirely. Studying these systems not only sheds light on the behavior of neutron stars, but also provides insights into the broader processes of stellar and planetary evolution. By observing how neutron stars interact with their companions, scientists can learn more about the forces that shape the universe, from the formation of stars and planets to the dynamics of binary systems. Each discovery brings us closer to understanding the complex and often unpredictable nature of these cosmic relationships. As we continue to explore the mysteries of neutron star companions, we are reminded of the intricate connections that bind the universe together. From the birth of stars to the formation of planets, every object in the cosmos plays a role in the grand tapestry of existence. Next, we'll delve into the enigmatic process of aging in neutron stars and the factors that influence their lifespans. Now shifting our gaze to the passage of time in the cosmos, we encounter the intriguing mystery of neutron star ages. How do scientists determine the age of these dense remnants? And why do some neutron stars seem to defy the expected timeline of aging? The answers lie in the interplay of magnetic fields, rotation, and the unique conditions that govern these celestial objects. Estimating the age of a neutron star is no simple task. Unlike stars that burn brightly for billions of years, neutron stars are born from the explosive deaths of massive stars, and their aging process is far more complex. One common method scientists use to estimate a neutron star's age is by measuring its rotation speed. Neutron stars, particularly pulsars, slow down over time as they lose energy through radiation and particle emissions. By calculating how much a pulsar has slowed since its birth, researchers can make an educated guess about its age. However, this method isn't foolproof, as some neutron stars appear to slow down at unexpected rates, leaving scientists puzzled. Another clue to a neutron star's age lies in its magnetic field. Over time, the magnetic fields of neutron stars weaken, a process known as magnetic field decay. By measuring the strength of a neutron star's magnetic field, scientists can infer how long it has been active. Yet, here too, mysteries arise. Some neutron stars exhibit magnetic fields that decay much faster than predicted, while others seem to retain their strength far longer than expected. This inconsistency challenges our understanding of how magnetic fields evolve in these extreme environments. Adding to the complexity is the role of a neutron star's environment. Neutron stars in binary systems, for example, can experience interactions with their companions that alter their rotation and magnetic fields, making it harder to determine their true age. Similarly, neutron stars that accrete material from surrounding space may appear younger than they actually are, as the influx of matter can temporarily rejuvenate their magnetic fields and spin rates. The mystery deepens when we consider neutron stars that appear much older or younger than their surroundings. Some neutron stars are found in regions of space where the surrounding material suggests they should be ancient, yet their rotation and magnetic fields indicate they are relatively young. Conversely, others appear to have aged rapidly, with weak magnetic fields and slow rotation rates despite being in regions where they should still be in their prime. These anomalies suggest that there are factors at play in neutron star aging that we have yet to fully understand. One leading theory is that the interiors of neutron stars may contain exotic states of matter, such as superfluids, which could influence their rotation and magnetic field evolution. Superfluids, which flow without friction, might allow the star's core to rotate at a different rate than its crust, creating discrepancies in observed rotation speeds. Additionally, interactions between the star's magnetic field and its superfluid interior could accelerate or delay magnetic field decay, further complicating age estimates. As we unravel the mystery of neutron star ages, we gain not only a deeper understanding of these fascinating objects, but also insights into the broader processes that govern the universe. The aging of neutron stars is a window into the behavior of matter under extreme conditions, offering clues about the fundamental forces that shape the cosmos. Each discovery brings us closer to solving the puzzle of why some neutron stars seem to age in ways that defy our expectations. With this mystery still unfolding, we now turn our attention to the powerful winds of particles that some neutron stars emit, and the role these winds play in shaping the surrounding space. Now shifting our focus to the dynamic forces at play in the cosmos, we delve into the mystery of neutron star winds. These high-speed streams of particles racing outward from certain neutron stars are not only breathtaking in their intensity, but also shrouded in questions about their origins and effects on the space around them. Neutron star winds are among the most powerful outflows in the universe, capable of reaching speeds close to the speed of light. These winds are composed of charged particles, primarily electrons and protons, which are accelerated to incredible velocities. But how are these winds generated? The leading theory points to the intense magnetic fields and rapid rotation of neutron stars. As a neutron star spins, its magnetic field can act like a cosmic generator, converting rotational energy into electromagnetic forces that propel particles outward. However, the exact mechanisms behind this process remain unclear, leaving scientists to wonder what other factors might be at play. One of the most puzzling aspects of neutron star winds is their variability. Some neutron stars produce steady, consistent winds, while others exhibit erratic bursts of particle emissions. This inconsistency suggests that the conditions within and around the neutron star play a significant role in shaping the wind's behavior. For instance, neutron stars in binary systems where they orbit another star may experience interactions that disrupt or enhance their winds. Similarly, the presence of accretion disks, rings of material spiraling onto the neutron star, could influence the wind's intensity and structure. The impact of neutron star winds on the surrounding interstellar medium is equally fascinating. These winds carry immense energy, capable of heating and ionizing the gas and dust in their path. Over time, they can carve out vast cavities in the interstellar medium, shaping the environment around the neutron star. In some cases, neutron star winds are so powerful that they can trigger the formation of new stars by compressing nearby gas clouds. Yet, the full extent of their influence remains a mystery, as the interplay between neutron star winds and their surroundings is complex and not yet fully understood. Adding to the intrigue is the connection between neutron star winds and other cosmic phenomena, such as gamma-ray bursts and fast radio bursts. Some scientists speculate that the sudden release of energy in these events could be linked to the behavior of neutron star winds. For example, a sudden change in the wind's intensity or direction might produce a burst of radiation detectable across vast distances. However, this remains speculative, and further observations are needed to confirm such connections. As we explore the mystery of neutron star winds, we uncover not only the forces that drive these cosmic outflows, but also their profound impact on the universe. These winds are more than just streams of particles. They are sculptors of space, shaping the environments around them and influencing the evolution of galaxies. Each discovery brings us closer to understanding how these winds are generated and how they contribute to the dynamic tapestry of the cosmos. With this mystery still unfolding, we now turn our attention to the phenomenon of light echoes around neutron stars, where reflections off nearby dust clouds reveal hidden details about these enigmatic objects. Now stepping into the realm of cosmic reflections, we uncover the mystery of neutron star echoes. These fascinating phenomena occur when light from a neutron star bounces off nearby clouds of dust, creating a kind of cosmic echo that reveals hidden details about the star and its surroundings. Imagine a flashlight shining into a foggy night. The light scatters and reflects, illuminating the haze. In much the same way, neutron star echoes provide astronomers with a unique tool to study these enigmatic objects. The process begins when a neutron star emits a burst of light, often in the form of X-rays or gamma rays. As this light travels through space, it encounters clouds of dust and gas. Some of the light is absorbed, but a portion is scattered in different directions, creating what we call a light echo. These echoes can appear as faint, glowing rings or arcs around the neutron star, expanding outward over time. By analyzing the timing, brightness, and structure of these echoes, scientists can piece together information about the neutron star's past activity and the environment it inhabits. One of the most intriguing aspects of neutron star echoes is their ability to act as cosmic time capsules. Because light travels at a finite speed, the echoes we observe today may have originated from events that occurred hundreds or even thousands of years ago. For example, a sudden flare or explosion from the neutron star could leave behind a series of echoes that reveal the star's behavior during that event. This allows astronomers to study the history of neutron stars in a way that would otherwise be impossible. But the mystery deepens when we consider the nature of the dust clouds themselves. These clouds are not uniform. They vary in density, composition, and distance from the neutron star. This variability affects how the light echoes are produced and observed. Some echoes may appear sharp and well-defined, while others are faint and diffuse. Understanding these differences is key to unlocking the secrets of the neutron star's environment and the processes that shape it. Another layer of intrigue lies in the connection between neutron star echoes and other cosmic phenomena. For instance, echoes have been observed following gamma-ray bursts, some of the most energetic events in the universe. By studying the echoes associated with these bursts, scientists hope to gain insights into the mechanisms that power them and the role neutron stars play in such cataclysmic events. Yet, much remains unknown, and each new observation raises as many questions as it answers. As we explore the mystery of neutron star echoes, we are reminded of the intricate interplay between light, matter, and time in the cosmos. These echoes are not just fleeting reflections, they are windows into the past, offering glimpses of the dynamic and ever-changing universe. With each discovery, we come closer to understanding the life cycles of neutron stars and their profound impact on the fabric of space. With this mystery still echoing in our minds, we now turn our attention to the decay of neutron star magnetic fields, a process that holds clues to the evolution of these stellar remnants. Now shifting our gaze to the enigmatic process of magnetic field decay, we delve into the mystery of how neutron stars lose their immense magnetic power over time. Neutron stars are born with some of the strongest magnetic fields in the universe, often trillions of times more powerful than Earth's. Yet, these fields don't remain constant. They gradually weaken, and the rate at which this happens varies dramatically from star to star. This raises a compelling question. Why do some neutron stars lose their magnetic strength faster than others, and what does this mean for their evolution? At the heart of this mystery lies the complex interplay between the neutron star's interior and its magnetic field. The magnetic field is thought to be generated by the motion of charged particles within the star's superfluid core. Over time, as the star cools and its internal dynamics change, the magnetic field begins to decay. However, the rate of this decay isn't uniform. Some neutron stars, particularly older ones, show signs of significantly weakened fields, while others retain their magnetic strength for much longer. This discrepancy has puzzled scientists for decades. One leading theory suggests that the decay rate depends on the star's initial magnetic field strength and its rotation speed. Neutron stars with stronger initial fields may experience faster decay due to the immense energy required to sustain them. Similarly, rapidly spinning neutron stars might lose their magnetic fields more quickly as their rotation slows down over time. Yet, this theory doesn't fully explain the observed variations, leaving room for other factors to come into play. Another possibility involves the neutron star's crust, the solid outer layer that encases its superfluid core. The crust is thought to play a crucial role in anchoring the magnetic field. If the crust undergoes changes such as cracking or rearranging due to starquakes, it could accelerate the decay of the magnetic field. Additionally, interactions with nearby matter such as gas or dust might also influence the field's strength over time. These interactions could strip away the magnetic energy, causing it to fade more rapidly. The implications of magnetic field decay are profound, as it directly affects the neutron star's evolution and behavior. A decaying magnetic field can alter the star's ability to emit radiation, influence its interactions with surrounding matter, and even determine its ultimate fate. For instance, neutron stars with weaker magnetic fields may transition into a quieter phase, emitting less radiation and becoming harder to detect. On the other hand, those that retain their magnetic strength might continue to produce powerful emissions, such as X-rays or gamma rays, for much longer. Understanding this process is not just about solving a cosmic puzzle, it's about piecing together the life story of neutron stars. By studying how and why their magnetic fields decay, scientists can gain insights into the internal workings of these stellar remnants and how they evolve over billions of years. Each observation brings us closer to unraveling the intricate dance between magnetism, rotation, and time in the life of a neutron star. As we ponder the fading magnetic fields of these cosmic powerhouses, we prepare to explore another layer of their complexity, the phenomenon of neutron starquakes, where the star's surface undergoes dramatic shifts, releasing immense energy and reshaping its structure. Now turning to the dramatic phenomenon of neutron starquakes, we uncover another layer of these cosmic giants' complexity. Imagine a star so dense that its surface is a solid crust, yet beneath it lies a superfluid core. This crust, though incredibly strong, isn't immune to cracking under the immense pressures and stresses it endures. When it does, the result is a starquake, a seismic event that can release more energy in a fraction of a second than the Sun emits in thousands of years. What triggers these colossal quakes? The answer lies in the neutron star's ever-changing structure. As the star spins, its crust experiences immense strain, especially if the star is slowing down or if its interior is shifting. Over time, this strain builds up until the crust can no longer withstand it, causing it to fracture. These fractures aren't just minor cracks, they can be massive, reshaping the star's surface and releasing bursts of energy that ripple through space. One of the most intriguing aspects of starquakes is their connection to the neutron star's magnetic field. The crust is thought to play a key role in anchoring the magnetic field, so when a quake occurs, it can disrupt the field's structure. This disruption can lead to sudden changes in the star's emissions, such as X-rays or gamma rays, which astronomers can detect from Earth. In some cases, these quakes have even been linked to mysterious phenomena like fast radio bursts, adding another layer of intrigue to their study. But the mystery doesn't end there. Scientists are still trying to understand why some neutron stars experience frequent quakes while others remain relatively stable. One theory suggests that younger neutron stars, which are still cooling and settling, might be more prone to quakes as their interiors adjust. Another possibility is that the presence of a strong magnetic field, particularly in magnetars, increases the likelihood of crustal fractures. Yet, even with these theories, the exact mechanisms behind starquakes remain elusive. The energy released during a starquake is staggering. In just a fraction of a second, a single quake can unleash energy equivalent to millions of nuclear bombs. This energy doesn't just reshape the star's surface, it can also send shockwaves through the surrounding space, potentially affecting nearby objects or even triggering other cosmic events. For astronomers, these quakes provide a rare glimpse into the internal dynamics of neutron stars, offering clues about their structure, composition, and evolution. As we explore the mystery of neutron star quakes, we're reminded of just how dynamic and unpredictable these stellar remnants can be. Each quake is a testament to the immense forces at play within a neutron star, forces that continue to challenge our understanding of the universe. With every new observation, we inch closer to unraveling the secrets of these cosmic tremors and the stars that produce them. Looking ahead, we prepare to delve into another fascinating aspect of neutron stars, the possibility of superfluidity within their cores, where matter behaves in ways that defy our everyday understanding of physics. Now shifting our gaze to the enigmatic interiors of neutron stars, we encounter the intriguing possibility of superfluidity, a state of matter that defies our everyday understanding of physics. Deep within these cosmic giants, neutrons may flow without friction, behaving like a superfluid. This phenomenon, while strange to us, could hold the key to understanding some of the most puzzling behaviors of neutron stars, from their rotation to their magnetic fields. Superfluidity occurs when particles, in this case neutrons, move in perfect unison, creating a frictionless flow. In the extreme conditions of a neutron star's core, where densities reach unimaginable levels, neutrons might transition into this exotic state. But how does this affect the star as a whole? One of the most striking consequences is its impact on the star's rotation. As the superfluid neutrons move, they can transfer angular momentum to the star's crust, causing subtle changes in its spin. This could explain why some neutron stars exhibit sudden changes in their rotation rates, a phenomenon known as glitches. The connection between superfluidity and magnetic fields adds another layer of mystery. Neutron stars are known for their incredibly strong magnetic fields, and the superfluid core might play a crucial role in generating and maintaining these fields. As the superfluid neutrons swirl and interact, they could create currents that amplify the star's magnetic field. However, the exact mechanisms remain unclear, leaving scientists to wonder how these two phenomena, superfluidity and magnetism, are intertwined. One of the biggest challenges in studying neutron star superfluidity is the sheer difficulty of observing it directly. The interiors of neutron stars are hidden from view, shielded by their dense crusts. Instead, scientists rely on indirect evidence such as the star's rotational behavior and the emission of X-rays or gamma rays to infer the presence of superfluidity. Even then, the data is often ambiguous, leaving room for multiple interpretations and theories. The implications of superfluidity extend beyond neutron stars themselves. If confirmed, it could provide insights into the behavior of matter under extreme conditions, shedding light on fundamental physics questions. For instance, understanding how neutrons behave in such environments could help us unravel the mysteries of quantum mechanics and the nature of matter itself. As we delve into the mystery of neutron star superfluidity, we're reminded of how much we still have to learn about these cosmic enigmas. Each discovery brings us closer to understanding the intricate dance of particles within their cores, a dance that shapes the very fabric of the universe. With every new observation and theoretical breakthrough, we inch closer to unraveling the secrets of superfluidity and its role in the life of a neutron star. Looking ahead, we prepare to explore another captivating mystery: the potential interactions between neutron stars and dark matter, a topic that could redefine our understanding of both these cosmic phenomena. Now turning to one of the most speculative and intriguing mysteries of neutron stars, we explore the possibility of their interactions with dark matter. Dark matter, the invisible substance that makes up a significant portion of the universe's mass, has long eluded direct detection. Yet, its presence is inferred through its gravitational effects on galaxies and cosmic structures. Could neutron stars, with their immense gravitational pull and dense interiors, hold clues to understanding dark matter? This question opens a fascinating chapter in the study of these cosmic objects. Neutron stars, with their extreme densities and strong gravitational fields, might act as natural traps for dark matter particles. As dark matter passes through a neutron star, it could be captured by the star's gravity, accumulating over time. But what happens next? Some theories suggest that dark matter particles could collide with the neutrons in the star's core, releasing energy and potentially altering the star's internal dynamics. This interaction could lead to observable effects, such as changes in the star's temperature or rotation rate, providing indirect evidence of dark matter's presence. The mystery deepens when we consider how dark matter might influence the evolution of neutron stars. If dark matter accumulates in sufficient quantities, it could affect the star's structure and stability. For instance, the additional mass from dark matter might accelerate the star's cooling process or even trigger its collapse into a black hole. These speculative scenarios challenge our understanding of both neutron stars and dark matter, pushing the boundaries of astrophysics. One of the most exciting aspects of this mystery is the potential to use neutron stars as cosmic laboratories for studying dark matter. By observing how neutron stars behave over time, scientists might detect subtle anomalies that point to dark matter interactions. For example, unexpected variations in a neutron star's spin or temperature could hint at the presence of dark matter particles within its core. These observations, combined with theoretical models, could help us unravel the nature of dark matter and its role in the universe. However, the challenge lies in distinguishing the effects of dark matter from other phenomena that can influence neutron stars. The dense environments of these stars are already complex, with processes like superfluidity, magnetic fields, and starquakes playing significant roles. Isolating the signature of dark matter requires precise measurements and innovative approaches, making this one of the most difficult mysteries to solve. As we ponder the potential interactions between neutron stars and dark matter, we're reminded of how much remains unknown about the cosmos. These interactions, if confirmed, could bridge the gap between the visible and invisible universe, offering insights into the fundamental nature of matter and gravity. With each new observation and theoretical breakthrough, we move closer to understanding not just neutron stars, but the very fabric of the universe itself. Looking ahead, we prepare to explore the final mystery in our journey: the life cycle of neutron stars, from their explosive births to their ultimate fates. This exploration will tie together the many threads we've uncovered, offering a comprehensive view of these enigmatic cosmic objects. Now, as we approach the final chapter of our exploration, we turn our attention to the life cycle of neutron stars, a journey that spans billions of years and holds profound mysteries about their ultimate fate. Neutron stars are born in the fiery aftermath of supernova explosions, where the core of a massive star collapses under its own gravity, compressing matter to unimaginable densities. This violent birth marks the beginning of their existence as some of the most extreme objects in the universe. But what happens to neutron stars as they age? Over time, these cosmic remnants cool and lose their rotational energy, gradually slowing down. Yet the details of their evolution remain shrouded in mystery. Some neutron stars may continue to spin for billions of years, their magnetic fields weakening as they age. Others might undergo dramatic transformations, such as accreting matter from a companion star or experiencing starquakes that reshape their surfaces. The question of how neutron stars change over such vast timescales is one of the great puzzles in astrophysics. One of the most intriguing mysteries is whether neutron stars eventually collapse into black holes. While neutron stars are incredibly dense, they are held up by a delicate balance of forces, including the pressure of neutrons and the repulsion of quantum particles. However, if a neutron star gains too much mass, whether through accretion or other processes, it could cross a critical threshold and collapse into a black hole. This raises the question, how common is this fate and what triggers it? Observations of neutron stars in binary systems, where they interact with companion stars, provide some clues, but the full picture remains elusive. Another aspect of the neutron star life cycle that puzzles scientists is their ultimate cooling process. As neutron stars age, they radiate away their heat, but the rate at which this happens is not fully understood. Some theories suggest that exotic particles or unknown processes within their cores could accelerate or slow down this cooling, adding another layer of complexity to their evolution. Understanding how neutron stars cool over billions of years could reveal new insights into the nature of matter under extreme conditions. The life cycle of neutron stars also ties into their role in the cosmos. These objects are not just relics of stellar death. They are active participants in the universe's evolution. Through processes like neutron star collisions, they contribute to the creation of heavy elements like gold and platinum, enriching the cosmos with the building blocks of planets and life. Their powerful magnetic fields and energetic emissions shape the surrounding space, influencing the interstellar medium and the formation of new stars. As we reflect on the life cycle of neutron stars, we are reminded of how much remains to be discovered. From their explosive births to their enigmatic fates, these objects challenge our understanding of physics and the universe. Each stage of their existence holds clues to fundamental questions about matter, gravity, and the cosmos itself. With every new observation and theoretical breakthrough, we inch closer to unraveling the mysteries of neutron stars and their place in the grand tapestry of the universe. This concludes our journey through the 25 mysteries of neutron stars and pulsars, but the exploration is far from over. The cosmos continues to beckon, offering endless opportunities for discovery and wonder. Stay curious, keep exploring, and join us as we delve deeper into the mysteries of the universe in future videos. Don't forget to subscribe, hit the notification bell, and share your thoughts in the comments below. Until next time, keep looking up. Now turning to the broader significance of neutron stars, we find that these cosmic powerhouses play a pivotal role in shaping the universe. Beyond their enigmatic nature, neutron stars are key players in the grand cycle of cosmic recycling. When massive stars explode as supernovae, they scatter their enriched material into space, seeding the interstellar medium with the building blocks for new stars, planets, and even life. Neutron stars, born from these cataclysmic events, continue this process by contributing heavy elements like gold, platinum, and uranium through their collisions and interactions. These rare and precious elements, forged in the extreme conditions of neutron star mergers, are scattered across the cosmos, eventually finding their way into the formation of planets and the chemistry of life itself. But the influence of neutron stars doesn't stop there. Their powerful magnetic fields and energetic emissions shape the surrounding space, influencing the dynamics of the interstellar medium. These emissions can trigger the collapse of gas clouds, leading to the birth of new stars and star systems. In this way, neutron stars act as cosmic architects, indirectly guiding the formation of galaxies and the evolution of stellar populations. Their presence in binary systems, where they interact with companion stars, further amplifies their impact, creating some of the most energetic phenomena in the universe, such as X-ray bursts and gamma-ray flares. Moreover, neutron stars serve as natural laboratories for testing the laws of physics under extreme conditions. Their immense density and strong gravitational fields provide unique insights into the behavior of matter and the nature of spacetime itself. By studying neutron stars, scientists can probe the limits of quantum mechanics, general relativity, and nuclear physics, pushing the boundaries of our understanding of the universe. Their role in producing gravitational waves, first detected in neutron star collisions, has opened a new window into the cosmos, allowing us to observe the universe in ways previously unimaginable. As we consider the broader role of neutron stars, it becomes clear that these objects are not just relics of stellar death but active participants in the ongoing story of the universe. They connect the life cycles of stars, the formation of galaxies, and the creation of the elements that make up our world. Their influence extends far beyond their compact size, shaping the cosmos on both local and cosmic scales. By unraveling the mysteries of neutron stars, we gain a deeper appreciation for their role in the intricate web of cosmic evolution and the profound interconnectedness of all things in the universe. As we look ahead to the future of neutron star research, the tools and technologies at our disposal are more advanced than ever before. Gravitational wave detectors like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have revolutionized our ability to observe the universe. These instruments allow us to detect the ripples in spacetime caused by cataclysmic events, such as neutron star collisions, providing unprecedented insights into the behavior of matter under extreme conditions. The detection of gravitational waves from neutron star mergers has not only confirmed theoretical predictions, but also opened up new avenues for studying the universe in ways that were once thought impossible. In addition to gravitational wave detectors, space telescopes are playing a crucial role in advancing our understanding of neutron stars and pulsars. Missions like the Neutron Star Interior Composition Explorer, or NISA, mounted on the International Space Station, are designed to study the interiors of neutron stars by measuring their X-ray emissions. These observations help scientists probe the exotic states of matter that exist within these dense objects, shedding light on the fundamental properties of nuclear matter and the nature of spacetime itself. Similarly, the European Space Agency's XMM Newton and NASA Chandra X-ray Observatory continue to provide high-resolution images and data, revealing the intricate details of neutron star environments and their interactions with surrounding matter. Another exciting frontier in neutron star research is the development of next-generation observatories, such as the Square Kilometre Array, or SCAR, which will be the world's largest radio telescope. Once operational, the SKA will have the sensitivity to detect faint pulsar signals from across the galaxy, potentially discovering thousands of new neutron stars and providing deeper insights into their magnetic fields, rotation rates, and evolutionary histories. This wealth of data will enable scientists to test theories about the formation and behavior of neutron stars with unprecedented precision. Moreover, advancements in computational modeling and artificial intelligence are transforming how we analyze the vast amounts of data generated by these missions. Sophisticated simulations allow researchers to recreate the extreme conditions of neutron stars in virtual environments, helping to predict their behavior and test hypotheses about their internal structures. Machine learning algorithms are also being employed to sift through massive datasets, identifying patterns and anomalies that might otherwise go unnoticed. These technological innovations are accelerating the pace of discovery, bringing us closer to unraveling the many mysteries that neutron stars and pulsars still hold. As we continue to push the boundaries of science and technology, the future of neutron star research promises to be as exciting as it is transformative. Each new discovery brings us closer to understanding these enigmatic objects and their role in the cosmos. With cutting-edge tools and a growing body of knowledge, we stand on the brink of uncovering answers to questions that have puzzled scientists for decades, and perhaps even posing new ones that will inspire the next generation of explorers. The journey to decode the secrets of neutron stars is far from over, and the possibilities are as vast as the universe itself. Now shifting our gaze to the cultural realm, neutron stars and pulsars have not only fascinated scientists but have also ignited the imaginations of storytellers, artists, and dreamers across the globe. These cosmic enigmas, with their extreme densities, rapid spins, and powerful magnetic fields, have become a source of inspiration for countless works of science fiction. From novels to films, neutron stars often serve as backdrops for tales of exploration, survival, and the unknown. Their mysterious nature makes them perfect symbols of the vast, uncharted frontiers of space, embodying humanity's curiosity and desire to explore the cosmos. In literature, neutron stars have been featured in iconic works like Arthur C. Clarke's The Neutronium Alchemist, where their immense gravitational pull and exotic matter play pivotal roles in the narrative. Similarly, in the world of cinema, these celestial objects have appeared in blockbuster films, often depicted as dangerous yet awe-inspiring phenomena that challenge the limits of human ingenuity. Their portrayal in popular media has helped bring the wonders of astrophysics to a broader audience, sparking interest in the science behind these captivating objects. Beyond fiction, neutron stars have also influenced the arts. Visual artists have drawn inspiration from their unique properties, creating stunning representations that blend scientific accuracy with creative interpretation. Pulsars, with their rhythmic flashes of light, have even inspired musical compositions where their precise beats are translated into soundscapes that echo the harmony of the universe. This fusion of science and art highlights the profound impact these objects have had on our cultural landscape, bridging the gap between the technical and the imaginative. In the realm of education and public outreach, neutron stars have become powerful tools for engaging the public with astronomy. Museums and planetariums often feature exhibits dedicated to these objects, using interactive displays and visualizations to explain their complex physics in an accessible way. Public lectures and documentaries frequently highlight neutron stars as examples of the universe's most extreme environments, captivating audiences with their mind-bending properties and the mysteries they hold. Even in everyday life, the influence of neutron stars can be felt. The term pulsar has entered popular lexicon, often used metaphorically to describe anything that emits regular, rhythmic signals. Their discovery has also shaped our understanding of time, as pulsars' precise rotations have been used to test theories of relativity and even inspire the design of highly accurate clocks. As we reflect on the cultural impact of neutron stars, it becomes clear that their allure extends far beyond the realm of science. They remind us of the beauty and mystery of the universe, inspiring creativity and curiosity in equal measure. Whether through the pages of a novel, the strokes of a painting, or the rhythms of a song, neutron stars continue to captivate our collective imagination, proving that the wonders of the cosmos are as much a part of our culture as they are of our science. As we bring our journey through the 25 mysteries of neutron stars and pulsars to a close, it's impossible not to marvel at how much we've uncovered and how much remains shrouded in cosmic enigma. From their violent births in supernova explosions to their mind-bending densities, rapid spins, and unimaginable magnetic fields, these celestial objects continue to challenge our understanding of the universe. Each mystery we've explored, whether it's the strange behavior of X-ray pulsars, the origins of fast radio bursts, or the speculative existence of quark stars, reveals just how complex and awe-inspiring neutron stars truly are. Yet, for every question answered, countless more arise, reminding us that the cosmos is a place of endless wonder and discovery. The mysteries of neutron stars and pulsars are not just scientific puzzles. They are windows into the fundamental laws of physics and the extreme conditions that shape our universe. They remind us that even the most advanced technology and the brightest minds on Earth are still grappling with the profound questions these objects pose. What lies beneath their crusts? How do their magnetic fields decay over time? Could they hold clues to the nature of dark matter or the origins of heavy elements like gold? These are the questions that drive astronomers, physicists, and dreamers alike to keep exploring, keep questioning, and keep pushing the boundaries of what we know. As we reflect on these 25 mysteries, one thing becomes clear. The story of neutron stars and pulsars is far from over. With every new observation, every groundbreaking discovery, and every innovative theory, we inch closer to unraveling their secrets. But the universe, in its infinite complexity, always seems to have more to reveal, and that's what makes this journey so thrilling. The knowledge that there's always more to learn, more to explore, and more to inspire us. So, as we wrap up this exploration, I encourage you to stay curious. The universe is vast and its mysteries are endless. Whether you're a seasoned space enthusiast or just beginning to dip your toes into the wonders of astrophysics, there's always something new to discover. If you've enjoyed this deep dive into the mysteries of neutron stars and pulsars, don't forget to subscribe and hit the notification bell so you never miss out on future cosmic adventures. Together, let's keep exploring the wonders of the universe, one mystery at a time. Until next time, keep looking up. The stars have so much more to tell us.